Imagine a cosmic explosion so powerful it outshines the entire galaxy it resides in. This is a supernova, one of the most spectacular phenomena in the universe. They are the final, dramatic acts in the lives of stars, cataclysmic events of staggering proportions that shape the very fabric of the cosmos. And yet, their grandeur is not merely for show. Supernovas play a critical role in the life cycle of the universe, influencing the formation of new stars, galaxies, and even planets. In this exploration, we delve into the explosive deaths of stars, the supernovas. Before we dive into the mysteries of the cosmos, make sure to like, comment, and subscribe to our channel. Now, let's get started. So, what exactly is a supernova? Well, picture a star maybe 5 or 15 times the size of our sun, reaching the end of its lifespan. But instead of simply fading away, it goes out with a bang, a supernova. This astronomical phenomenon is essentially a massive explosion that occurs when a star has exhausted its nuclear fuel. Now there are different types of supernovas, each with its unique characteristics. First we have type Ia supernovas. These occur in binary star systems where one star is a white dwarf that's stealing matter from its companion. Then there are type Ib and type Ic supernovas, which occur when a massive star loses its outer layers of hydrogen-helium before exploding. Lastly, we have type II supernovas, which are the result of massive stars collapsing under their own gravity. These magnificent cosmic fireworks are the dramatic end to a star's long life. But how does a star reach this explosive end? Well, it's a tale as old as time itself, a cosmic dance that begins in the heart of a nebula, a vast cloud of dust and gas. Here gravity pulls matter together to form a star, igniting a nuclear furnace that burns for millions, even billions of years. This is the main sequence stage where stars like our sun spend most of their lives, fusing hydrogen into helium and radiating light and heat into the universe. However, for the most massive stars, this tranquil existence is merely a prelude to a more dramatic fate. When these giants exhaust their hydrogen fuel, they start fusing heavier elements, creating layers like an onion from helium to carbon, oxygen, neon, and so forth, all the way up to iron. But iron doesn't generate energy when fused, and so the star's core collapses under its own weight, setting the stage for a supernova. In a fraction of a second, the core rebounds, sending a shockwave ripping through the outer layers of the star. This detonation is so violent, so cataclysmic, that it can outshine an entire galaxy, briefly illuminating the cosmos before fading away. So, you see, the death of a star is not a quiet event, but a spectacular explosion, the end of one celestial journey and the birth of another in the endless cycle of stellar evolution. Now let us delve deeper into the explosion itself. A supernova is a celestial event of epic proportions, marking the catastrophic end of a star's life. But it's more than just an explosion. It's a staggering release of energy that outshines entire galaxies for weeks or even months. Imagine for a moment the energy that our sun will emit over its 10 billion year lifespan. Now, compress that energy into a brief period of several weeks. That's the power we're talking about when it comes to a supernova. It's an energy release so immense that it can briefly outshine an entire galaxy. But what's the impact of this energy on the surrounding space? Well, the force of the explosion propels the outer layers of the star into space at speeds of up to 20% the speed of light. This violent expulsion creates a shock wave that can trigger the formation of new stars in surrounding gas clouds. The core of the star, meanwhile, collapses under its own gravity. Depending on the initial mass of the star, this can result in either a dense neutron star or a black hole. The remnants of the explosion, enriched with heavier elements forged in the heart of the dying star, are scattered across the cosmos. These elements, ranging from oxygen and carbon to gold and uranium, are the building blocks for new stars, planets, and ultimately, life itself. A supernova explosion is one of the most energetic events in the universe. Not all supernovas are the same. Indeed, these explosive stellar events come in different flavors, each with its own unique characteristics and conditions. Let's delve into the main types, Type I and Type II supernovas. Type I supernovas lack the presence of hydrogen in their spectrum. This group is further subdivided into Type Ia, Type Ib, and Type Ic, each distinguished by different elements in their spectral lines. Type Ia supernovas are particularly interesting as they act as cosmic measuring sticks. They have a consistent peak brightness, which allows astronomers to calculate their distance from us with remarkable accuracy. These type Ia supernovas occur in binary star systems, where one star is a white dwarf. The dwarf star pulls matter from its companion until it reaches a critical mass, leading to a thermonuclear explosion. On the other hand, Type II supernovas are hydrogen-rich. These are the final acts of stars more than 8 times the mass of our Sun. When these massive stars exhaust their nuclear fuel, they can no longer support their own weight. The core collapses, leading to a shock wave that blows the outer layers of the star into space. Each type of supernova gives us a different piece of the cosmic puzzle. They help us understand the life cycles of stars, the elements they produce, and the ways they shape the galaxies they reside in. Whether Type 1 or 2, each supernova is a unique and fascinating event. Supernovas are not just spectacular to observe, they play a crucial role in the universe. These cosmic detonations are the universe's ultimate recycling program, taking the remains of a star and dispersing them across space, seeding the cosmos with elements that are critical for the formation of new stars, galaxies, and even planets. Think of it this way: every star is a cosmic kitchen, cooking up elements in its core. When a star goes supernova, it's like a pressure cooker exploding, scattering its stellar ingredients across the universe. These elements form cosmic clouds or nebulae, which eventually collapse under their own gravity to birth new stars and planetary systems. So, in essence, every atom in your body, the air you breathe, the ground beneath your feet, it all came from stars that lived and died billions of years ago. We are quite literally made of star stuff. But the impact of supernovas goes beyond just matter. The incredible energy released by a supernova can trigger the birth of new stars. The shockwave can compress the surrounding gas and dust, creating dense regions that eventually collapse to form new stars. Moreover, the remnants of supernovas, known as neutron stars or black holes, continue to intrigue scientists with their extreme conditions, providing us invaluable insights into the laws of physics under extreme conditions. Without supernovas, the universe as we know it would not exist. They are the cosmic engines of creation and destruction, shaping the universe one explosion at a time. These cosmic explosions have been a rich source of discovery for astronomers. Through their tireless observation of the celestial sphere, scientists have gleaned fascinating insights into the nature of supernovas. The study of supernovas is no small feat. It involves the use of powerful telescopes, both on the ground and in space, to capture the fleeting moments of these stellar explosions. Scientists then scrutinize this data, decoding the clues hidden in the light and energy of the supernova, to understand the life and death of stars. One of the most significant discoveries in astronomy came from observing a particular type of supernova known as Type Ia. These supernovas, born from white dwarf stars, always explode with the same brightness. This consistency led astronomers to a groundbreaking realization. Type Ia supernovas can be used as cosmic yardsticks, allowing them to measure vast distances across the universe. Another remarkable supernova event, the SN 1054, observed in the 11th century, gave birth to the Crab Nebula. This supernova was so bright that it was visible even during the day. Today, the remnants of SN 1054 serve as a dynamic laboratory for studying the physics of supernovas and the high-energy particles they produce. From revealing the universe's size to understanding the elements that make up our world, supernovas have proven to be cosmic beacons of knowledge. As we push the boundaries of our understanding, supernovas continue to captivate scientists and stargazers alike. In our journey today, we have explored the spectacular world of supernovas. We've delved into the intricate process of stellar evolution, learning how stars, in their cosmic splendor, journey from formation to their explosive ends. We've peered into the heart of the explosive event itself, marveling at the incredible energy supernovas release into the cosmos. We've differentiated between Type 1 and Type 2 supernovas, understanding the specific conditions leading to each unique explosion. We've also touched upon the profound impact supernovas have on our universe, contributing to the formation of new stars, galaxies, and even planets. Finally, we've highlighted how scientists study these cosmic fireworks and the significant discoveries they've made, illuminating our understanding of the universe. Supernovas, the explosive deaths of stars, are a testament to the ever-evolving dynamic nature of our universe. As we gaze up into the night sky, we can marvel at the grandeur of the universe and the explosive deaths of stars, the supernovas. If you enjoyed this cosmic journey and want to continue exploring with us, please subscribe and like our content. Your support helps us keep the universe at your fingertips.